Hi everyone, I'm Brian Demers, and this is JSON Web Tokens and PASETO and Macaroons, oh my. In this video, I'm going to talk about what security tokens are, specifically structured security tokens, and then I'm going to talk about three different types of tokens: JWTs, PASETO, and Macaroons. Along the way, I'll talk about how you would use them to secure your web applications. If you do a Google search for the term security tokens, the first thing you'll probably see is something like this. And I'm not here to talk about cryptocurrency. And if you do an image search for security token, you're going to find more pictures of Bitcoin and possibly some RSA hardware tokens. Now, it's been a long time since I've had to use one of these tokens, but you get the idea. The term security token is a bit abstract. So usually you're going to have better luck Googling for something specific, like a specific token type, like JWT Authentication or JWT Security Token. That should help you avoid getting results for things like finance-related securities. I think one of our collective missions as software developers is to make it hard for others to Google for things. So this talk is about the formats you would use to secure your web applications, either between a client and server or various microservices. I'm going to focus on the talks themselves and gloss over how you actually get the token. If you're interested in that, there are whole talks devoted to how you get tokens with OAuth and other protocols. So what is a security token? These tokens are usually temporary strings that grant you access to some resource. Usually you get them by exchanging a long-term credential, like a password, for a short-term credential, this token. Typically, like when you log into a website, you exchange your password for a cookie. And then every time you communicate back to the server, you use this token. So let's take a step back with a quick refresher on cookies. So this is my favorite cookie recipe. You take your ingredients, the username and password, and you put them in a large server and you mix. And then you bake them in a database for 350 degrees for about 10 minutes. And then you serve them warm with a nice cold glass of milk, right? All right, so kidding aside, you submit your credentials, your username and password or whatever it may be. The server then validates them. Assuming they're good, it creates a session ID and stores that in a database or some other store. The response then contains a set cookie header, which is just a key value pair. In my case, session equals, and then this random looking string. This header tells your browser that whenever you communicate with that server, you need to send along this cookie. And that looks something like this. My next request would contain the cookie header. This time, instead of validating my username and password, the server then looks up my session in a database, and assuming all is well, the server sends me back the web page I asked for. This works well for a lot of cases, but less so when you start to talk about APIs or the need to make endpoints stateless. If you're more of a CLI fan, the previous example would look like this. You log in with a username and password. The message is sent to the server. It has your username and password in the authorization header using basic auth, which is just base64 encoded, so essentially plain text. This server then responds with a set cookie header, assuming you were able to log in. And again, we see that key value pair of the session ID. And then anytime you communicate back with the server, you send the cookie in place of your credentials. Enough with cookies. My baking skills are a little weak, so I'm going to switch to the keycard analogy. You may not remember this, but in the before times, we had these things called hotels. And since we're doing everything virtual, my example is going to be a virtual hotel. So when you check into your hotel, you show them your credentials, an ID and a credit card. Mostly they only care about the credit card, and they give you the key card in return. And my room can be opened by anyone with that card. They're the bearer of that key. The previous cookie examples used an opaque value. If I wanted information about my account, I needed to ask the server for that info and pass along my cookie with the request. With a structured security token, there's data inside. I could create a token that contains these values. guest B Demers, room 1337, and so on. But more important than the data, we need to be able to verify the token itself. And this is done with cryptography instead of the cookie example, which was looking it up in a database. Anytime there's data in a token, you need to validate the token before reading its contents. Otherwise, you don't know if you could trust that data or not. Maybe an attacker could have changed something or spoofed it. In the case of our virtual hotel, I don't want random people creating hotel keys for my room. We only want to allow keys that were issued by the front desk. All right, so putting this all together, this means because we can validate a token, they can be used to statelessly authorize a user. All right, so how do you use a token? So let's go back to our previous example. And this time we're going to replace the cookie header with a token. And this is typically an authorization header with the bearer prefix. Remember I mentioned the bearer of this token can access the resource. Now this token is actually going to be, represent my hotel keycard. So my virtual keycard. And instead of verifying the cookie in a database, we're going to use cryptography to verify the token locally. This will remove the need to go access the database. Now, how you do that verification actually depends on the individual token formats, and we'll get to that in a minute. And while we're here, it's also worth mentioning you cannot replace all your cookie use cases with these tokens. The simplest reason for this is in the case of a user logging out. You want to make sure you invalidate any sessions associated with the user when they log out, and you can't do this with a security token. They're stateless. You would need to keep track of all these revoked tokens in a database and then look them up every time you contact the server. And then we're back to something that looks like this, right? This time with more complexity. Now, there are some other ways to mitigate this. This isn't the only option of the technique you could use. You could use short-lived tokens, something that only lasts for a few minutes. That way, if somebody logs out, the maximum exposure time is a couple minutes, and that may be acceptable, especially for APIs. Or any read-only operations, you could validate the token locally, and any request that mutates or changes the data, you look to see if that token has been revoked. So let's get into actual token formats. I'm going to start with JWT because it's by and far the most popular. 99% of the time, whenever anyone mentions JWT, we're actually talking about a JWS, which is a JSON Web Signature. There are also JWEs that are encrypted. These formats are defined in a set of specifications called JOSE, or JavaScript Object Signing and Encryption. Now, you may see JOSE maybe on your JWT library, or parsing libraries may mention JOSE in the name. That's how you know it also refers to JWTs. Okay, so let's take a closer look at JWTs. Okay, so let's look at a JWT. I'm going to use the same data as before, same name, same room number, everything, etc. But everything else is going to be a little different. So let's walk through a JWS. So a JWS contains three parts. We have a header, the payload, and this last bit on the end is the signature. And that was created using a signing key. Each of these sections is base64 URL encoded, and they're all separated by a period. So this means the first two sections you could just copy and paste into your favorite base64 decoder. I'm going to use Code Beauty, and this will get back my JSON string with all of the white space removed. And I can do the same thing with the second bit here. And that'll be the payload JSON as well. So as you can see, it's the same content with just the white space removed. So that's why it's important to make sure you treat your JWTs just like you would treat plain text. You shouldn't store any secrets in them, and you need to protect your JWT. A JWS has a signature, and there's three different types of algorithms you can use. You have a shared secret, so that creates HMACs. You have public keys, so you have a public and private key, and you have the none option. You never want to use the none option. That removes the signature. That removes the S from the JWS, which means you basically just have JSON. So switching back to an HMAC. So as I mentioned before, the contents of the header and the payload are just JSON, and we refer to the name-value pairs as claims. And there are three different types of claims. There are registered claims. Those are the keys that are defined in the JWT specs. So for example, type, key ID, subject, those are all registered claims. And then there are public claims as well. Public claims are defined by other protocols, and they're registered in an official IANA registry. So for example, OpenID Connect defines this name claim, and then everything else is a private claim, which means in my case, I have room. Room isn't defined anywhere. That's for my own use case. You need to watch out when you use private claims that you don't conflict with any public or registered claims. The actual algorithm that's used to sign the token is defined in the header, along with an optional key ID. If you have multiple keys, you need some sort of hint as to which key to use when you later validate the token. And of course, it's a good idea to rotate your keys from time to time, so using a key ID is very handy. So moving on to the payload of this token, we see we have a subject. The subject is a registered claim, and that defines the target of the token. In this case, it's me. I'm the guest at this virtual hotel. It also contains my name and my room number. Again, this is a private claim. And then we have some date values. So this token has an NBF, which is not before, and it has an EXP, which is the expiration. These dates are an epoch seconds format, which means it's the number of seconds since the epoch. You may have to watch out when using these date values. Many programming languages assume that epoch dates are in milliseconds. So if you want to use one of these dates, you need to multiply it by 1,000 first. All right, so how do you actually go about validating a JWT? So first things first is you decode this header. Once the header is decoded, you look at the algorithm. From there, you know what kind of crypto you're using. As I mentioned before, you may need to use the key ID to look up the key that was used to sign the token. Once you have an algorithm and your key, you can then calculate the signature of these first two sections. If that matches this last section, then you can move on to validating the payload. You base64 URL decode the payload, you parse the JSON, and then you look at these dates. You need to make sure the current date is within the not before and the expiration date. And if everything is valid there, then the JWT is valid. Then you can move on to using whatever contents of that token, and you can trust that data was sound. Remember, the data in a JWS should be treated like plain text. Anyone that sees this token has access to the data inside of it. For example, your browser plugins might have access to this data. I'm not going to spend a whole lot of time on JWEs. They're similar to JWS with the exception of having an encrypted payload. And there are a few other sections in the token that are all fed into the decryption algorithm. One easy way to tell the difference between a JWS and a JWE is to count the dots. A JWS at most will have 2 periods in the structure, and a JWE would have more than that. If you're using JWEs, let me know what you're doing with them in the comments or chat below. JWTs are everywhere. There are a ton of library options and framework integrations. But that doesn't mean it's without problems. In my opinion, there are too many options. JWTs are complicated. There are at least 9 different RFCs, and the more complex a system is, the more bugs you're likely to have. There are 13 different algorithms for JWS alone, and then 17 more for JWEs. That's 30 in total. And then there's that whole none algorithm thing I mentioned before. At that point, it's just JSON. Use JSON. If you're going to remove the signature from a JWS, what's the point? So this is where PASETO fits in. The PASETO format was created as a response to the problems and complexities of the Jose specs. With PASETO, you only have 4 options. Do you want your tokens encrypted or not? And then there are 2 versions. Version 1 is compatible with today's crypto libraries, and then V2 is based on emerging crypto standards. If a vulnerability was found in one of these formats, a new version format could be created to solve the issue. The general advice is to use V2 if your libraries support it, otherwise using V1 is fine. If you're new to PASETO, check out paseto.io. It's very similar to JWT. The token is dot separated base URL encoded, and the strings are broken up into 4 parts: the version, the purpose, the payload, which is the contents of the token, and then an optional footer. So let's walk through a token in more detail. Similar to before, we're going to use token.dev to debug our PASETO. Once again, we have the same token. This time it's formatted as a PASETO, so it looks a little different. But it contains the same data as that JWT. Instead of a header, we have a plain text version.purpose. So that's version.purpose, and in my case it's v2 and public. And the header of the JWT also contained a key ID, so if you need a key ID in a PASETO, that's been moved to an optional footer. So there are 2 purposes of a token. They're either local tokens or public tokens. Local tokens are encrypted and they always use a shared key. So anyone with a local copy of that key can read the contents of the token. Public tokens are not encrypted. They're the equivalent of a JWS, and they use a public key pair to create the signature. You may have also noticed that the date values look different. PASETO uses an ISO 8601 formatted string instead of epoch, which is a little easier on the eyes. So let's once again walk through this token. So we have a version, as I mentioned before, the purpose, the payload, and the footer. And this part that didn't get highlighted, that's actually the signature. Because PASETO is a fixed format, we don't need to separate every section with a dot. So if it's a V2 public token, it's always going to be formatted like this. So you take the last 64 bytes, and that's the signature. Of course, you can grab the contents of the token, and you can paste them into your favorite base64 decoder. So in my case, I'll grab the payload, and I'll paste that over here once again using code beautify. And you can see, again, we have a JSON object with the white space removed. So going back to my token, the payload is structured the same. You still have a subject. We actually have the same exact set of registered claims for PASETO that is used with JWT. The private claims are still the same. You need to watch out to make sure there's no conflict between the private claims and any registered claims. However, one thing of note, there is no official public registry of PASETO claims. The good news is, because the registered claims are identical to JWTs, you could actually use the IANA public registry for JWT claims in your PASETO tokens and you'd be fine. Let's quickly run through how you would verify a PASETO. First, you figure out which version you're using. That defines the format of the token as well as whatever your cryptographic needs are. Then the purpose, you're either going to decrypt a token or you're going to verify a signature of a token. In the case of a V2 public token, as I mentioned before, the signature is the last 64 bytes here. So I'm going to take all of the other sections and I'm going to calculate the signature based on that. And if it matches this signature, I can decode the payload and verify its contents. So just like a JWT, I base64 URL decode the JSON, then I parse it, and then I validate the dates. I need to make sure the current date, it falls in between the not before and the expiration date. If everything checks out there, I can use the data from the token in my application. PASETO covers the same set of use cases as JWT, but they're easier to use, which means there's less room for human error. One obvious exception to this is when the protocol that you're using explicitly calls for the use of JWT, like in the case of OpenID Connect. Then obviously you use what the protocol dictates. There are a couple of drawbacks as well. The PASETO RFC is still in draft state, and it's actually two different RFCs. One is strictly based on a newer crypto algorithm, which is independent of PASETO, and then the other one is the PASETO spec itself. So shameless plug, I work on libraries in both formats, JWT and PASETO. So if you're a Java developer, go check out JWT or JPASETO. Next up, we have macaroons. These are one of my favorite desserts, and depending on where you are in the world, macaroons are made a little different. But in the States, macaroons are typically made with coconut. However, for some reason, they're often confused with macarons. You know, it's only one letter difference. But if you do a Google search for macaroon, at least half the results are macarons. And if you do an image search, it's most of the results. I get it though. Given a choice between the two, you know, this looks a lot more fun than a coconut blob, right? The first two token types are very similar. This is the odd one out. Focus here is on delegation of authorization. And unlike the other formats, anyone with a macaroon can update it to reduce its scope. This is referred to as attenuation, and it allows flexible access control. I could get a macaroon and then reduce its scope before giving it to you, and then you could use it. All of this is accomplished by chaining together HMACs. An HMAC is a hash-based message authentication code. And a hash by itself is a one-way cryptographic function. That means there's no way to unhash something. If you hash a password, there's no way to recover that password. But in our case, the authentication bit is the important part. So let's take a look at an example. The first command calculates the hash of a string, and anyone with this string can do this. You may have used other tools to calculate checksums like SHA-SUM. It's the same thing, you get the same result. In the case of our tokens, if an attacker could change the actual token, they could probably also change the signature. So that's why the HMAC is important. So with an HMAC, we add a secret string, and that's the key. And that way, only people with the secret key can validate that hash. This forms the basis for macaroons. There is no official spec for macaroons, so let's walk through one at a high level. To create a macaroon, you start with a random value, that's the nonce, and a key. You keep this key a secret. And you use that key to calculate the HMAC of the nonce, and that gets you a signature. Then you encode this token, once again, usually base64 URL encoded, and then that's your token. We don't need to stop there. We can add restrictions to this token called caveats. First, we remove the signature from the token, and then add a caveat. In my case, this token is only good for room 1337. And then calculate another HMAC using the previous signature as the key. This gets you a new signature, and since it's the last signature that we have, we add that to the token. So now here's where things get interesting. I can take this token and give it to you, but before I do that, I'm going to only allow you to enter my room for the next 5 seconds. So once again, the first thing I do is I remove the signature from the token. Then I add another caveat. This time I'm going to restrict the time for 5 seconds. And then I'm going to calculate another HMAC. And then since it's the last one, I'm going to add that to the token. The important thing to remember here is that we're using the output of the previous HMAC as the input to the next. Okay, so it took me a bit to grok that, and it took me much longer to understand third-party caveats. So buckle up. Okay, so now I'm going to talk about how to verify or discharge a third-party caveat. This allows for third parties to use a macaroon, but they need to offer additional proof before they're allowed to use it. Okay, so remember we have a virtual hotel, and it has a door service with a secret key, and I'm staying at this hotel. And when I check in, they create a macaroon. Remember, we can calculate key 3 here by chaining together these HMACs. and then they give me the key to my room. But before long, I want to schedule the maid service. So I take my Macaroon and I'm going to add a couple different caveats to it. Okay, so remember, I know key 3 because it was in the original signature. So that means I can use that to update the token. My first caveat isn't anything special. The cleaning service can now only enter my room midday. But the next one is a bit more complicated. So I'm going to create a random key, poof, out of thin air. And I'm going to use this key to communicate with the other services without the cleaning service knowing the details. This digital hotel has a separate scheduling service because we have a lot of virtual rooms that all need to be cleaned and we can't all clean them at once. So I'm going to encrypt my key, key R, using the previous signature. Now only the door service can get access to that. And I'm going to do it again, but this time I'm going to use the public key of the scheduling service. And I'll also add some metadata about the cleaning service. So now both the hotel door service and the scheduling service have access to my key R. Now my Macaroon gets sent over to the cleaning service, but it can't do anything with it. So it takes that gray bit and sends it to the scheduling service. The scheduling service, remember, can decrypt that data to get my key. With that, it creates another Macaroon, and this time using key R as the initial HMAC input. Any additional caveats are chained in as well. In this case, the time has to be greater than 12:30 before my room will open. So now the cleaning service sends both Macaroons back to the door service. And the door service validates the first Macaroon. When it gets to the encrypted part, it decrypts my key R using key 4, remember, which it calculated from the previous line while verifying the token. It now has my key R. The gray part is opaque. It's just a stream of bytes to the door service. It can still be validated. You can take a stream of bytes and calculate the HMAC on that. However, with key R in hand, it can now go validate the discharge Macaroon. So it's going to walk through that one just like the other one, and it's going to use key R as the initial input. Okay, so you made it through that. Macaroons are super interesting and they offer a lot of potential power, especially for delegated auth use cases. But there are a few downsides. Macaroons are based on research from a Google white paper and there's no official spec. This means there's some potential for drift between implementations, like how various caveats are handled. The good news is there is a C-based implementation called libmacaroon, and that seems to have emerged as the de facto standard. And you just sat through my last slide, so you know third-party caveats are complex. So which one should you use? That depends, just like everything. Depends on what you're building. There's a lot of existing tooling for verifying JWTs, and we know from experience this matters more in some cases. Typically though, which format to use is not a client decision. Some server is going to hand you a token, and then you use some library to validate it. As with any library you use, especially security libraries, you need to make sure you're using something that's maintained and is kept up to date. All right, so I know this is a bit of a cop-out, but if you're building a service, you should probably use what's available already in the framework you are using. You don't want to build this stuff yourself, because friends don't let friends build auth. Okay, thanks everybody for watching. I hope you learned a bit about tokens and how they're used. And if you're watching this video in Octane, you can type any questions you have into the chat and we'll be here for a bit to answer them. And if you're watching this after Octane, maybe up on YouTube, leave a comment there and we'll get back to you over there. Thanks again.